propulsion devices. Here's two pictures of, one's of course a cartoon on the left, and the one on the right is an actual low thrust engine that's in NASA Glenn and their vacuum chambers. They turn that thing on, they leave it on for about a year, and they make measurements. These are devices that they emit a beam of ions or charged particles, and those particles are going very fast, 10 times faster than a hot gas in a typical chemical rocket engine. But as you can imagine, because of the momentum transfer, the thrust is much lower, much lower. Of course, you could never use this to leave the surface of the Earth. You can only use it once you're already in space. You turn this engine on, and you leave it on for weeks, months at a time, and the acceleration of the spacecraft builds up over time because it's constantly accelerating, but at a very low acceleration level. This is a schematic diagram of an electric engine, an ion engine, and I'm not an expert in this, but just to briefly explain what happens. You have some kind of propellant, usually a noble gas like xenon, and then it's bombarded with electrons to create positive ions, and those are then accelerated out the back with a charged grid. So it's just charged particles attracting each other, and then those ions shoot out the back, and they're going at a very fast speed, but again, that mass transfer, that momentum transfer is very low. A chemical rocket, you light some propellant, and it's going fast, and it's going out a nozzle, but you're throwing a lot of mass out the back, and that's where you get the thrust. Here, you have, again, very high velocity speed, but very low mass because they're just particles, they're just ions. Here's some basic equations. So the thrust of an electric propulsion engine is given by the top equation, and you can actually derive this from kinetic energy. You can look at the kinetic energy of the exhaust of this engine and then calculate the thrust from that equation. But it turns out it's 2 times the efficiency times the power divided by c, and c is the speed of the exhaust particles. Efficiency is how efficient this engine is at turning its power source, which a lot of times is a solar power array, into thrust. So that's an efficiency factor that's always less than 1. Typically it's 0.5, 0.6. These engines are about 60% efficient. The power is just simply the input power to the thruster in watts, and that's a function of how big the solar array is. So how much power can you get to the engine? And then C is the exhaust speed, and it's usually written in terms of this term called specific impulse, which is a characteristic of the type of propellant, the type of engine. And just to put it in perspective, chemical rockets have specific impulses between 3 and 400 seconds. And electric propulsion devices, there's 2 main devices, a Hall thruster and an ion engine, and they have specific impulses about 10 times higher. So at the high end, the ion engine has specific impulse around 3,000 seconds, 10 times greater than a chemical rocket. So if I take G, Earth gravity times ISP, the exhaust speed is 10 times higher. And that's where the efficiency comes from, the overall efficiency of these engines. So to put it into perspective, some applications of these devices, the concepts have been around since the 1960s, but it's only been recently that these engines have made their way onto actual spacecraft. They can be used for large energy changes, for changing the orbit. That hasn't been done yet so much. They can also be used for orbit repositioning, changing the phase of the satellite in a low Earth orbit or in a geostationary orbit. That hasn't been done. They're currently being used for that. What's called orbit maintenance, counteracting perturbations from either drag or solar radiation pressure or lunar solar gravity. That tends to knock a satellite out of its desired orbit just slightly, and you can use these devices because they're very efficient to get the satellite back into orbit. So, as I said, the majority of these applications have been for orbit maintenance, and that's the least demanding task. There are some examples, but the 2 major examples, Deep Space One actually used solar electric propulsion. In fact, that was the picture back here. That's Deep Space One. That's the engine for Deep Space One. On the right, of course, that's the cartoon of Deep Space One. And it used an electric engine to take the satellite from Earth out to 2 comets, Borelli and Wild. I think those are the two comets, back in 1998. So that was the first time it was ever used for interplanetary travel. And there's a current spacecraft, the Dawn mission, and it's currently at, I can't remember, it's either Vesta or Ceres. It's at one of those asteroids right now. And it will be leaving, I think, this summer to the next target. And I actually had some input to that mission a couple of years ago, to the Dawn mission. Okay, so let's now talk about orbit maneuvers. In all cases, it starts with the satellites on the Earth, and there's a launch vehicle that takes it into what's called a low Earth orbit. And then from there, really, you can go anywhere. You can go to higher orbits for whatever the application might be, or to the Moon, or to Mars, or the interplanetary type travel. Transfers between circular orbits is a common maneuver. So you start at a low circular orbit, and you want to go to a higher circle, like geostationary orbit. Maybe you've heard of this. Geostationary is an orbit that the period is about 24 hours. So you put a satellite there, and that's what communication satellites are, and they always look down at the same point on the Earth. And here's a diagram of a geostationary orbit. It is to scale. So there's the Earth. Low Earth orbit, you can't even see it. It says initial orbit. It practically hugs the Earth. It's only 200 kilometers above the surface. That's nothing. That's just barely above the atmosphere. Geostationary orbit is that big circle. That's the final orbit. And the problem is geostationary orbit is equatorial. So you want to get to the plane of the final orbit, but the initial orbit, if you launch from the United States, is inclined at 28.5 degrees because that's the latitude of Kennedy Space Center. So you have to go on this transfer orbit that goes north, I guess you would say, in the northern hemisphere. It's a three-dimensional transfer, and then half of an ellipse later, it hits the final orbit. And there's two impulses. There's an impulse marked delta V A at the beginning and delta V B to create the circular orbit. So that's how you generally do a transfer, but that's for the case of a chemical propulsion system. A chemical rocket providing a large velocity change.
So I might interrupt a few times here if it's okay. You guys remember we just learned about impulse, right? What is impulse? Anybody? Change in momentum. Right, but
I got that coming up on the next slide.
Oh, okay.
That very thing.
Okay,
Go ahead.
good. But it's per unit mass. That's why you delta V, but you're talking about it as an impulse.
And that's actually the next
Oh,
slide.
okay. Shut up, Ojikangas.
No, that's good to point that out. But here's a simple schematic of how an orbit transfer has to occur. You have to have, in this case, the red dashed ellipse has to, of course, intersect both orbits. If I want to go from the green orbit, the initial orbit, to the target orbit, the blue orbit, that's a feasible transfer, an ellipse that touches both orbits. And it turns out, and I'll show this here shortly, the best one is that ellipse that just is tangent to the bottom point on that green orbit, and it's tangent to the top point on the blue orbit. And as was indicated, you apply these impulses. You apply impulses noted here. Impulse 1, where it intersects the initial orbit, impulse 2 at the top orbit. So 2 birds, or 2 impulses, and then you've got the desired orbit and the transfer. So during that transfer, it's all coasting. There's no power propulsive maneuvers going on. So here's my slide with impulse. So if I just look at F equals ma, F, and I look at acceleration is approximately change in velocity over change in time. That's like a derivative of velocity, which is acceleration. F equals ma. Now solve that for the delta V. Force times delta time, that is impulse, and divided by mass. So it's like impulse per unit mass. That is delta V. That's my equation I could use to estimate how much velocity was imparted on the spacecraft instantaneously. So you assume that because the force is so high, that velocity just happens almost instantaneously. You fire a rocket, that rocket only fires for a few seconds, and then the velocity changes by a large amount to make the orbit transfer happen. So, and it turns out delta V this change in velocity can really be a measure of the performance of the maneuver, the amount of propellant needed. And you kind of see that in the equation. It's force times time, delta time. So if delta V is large, that meant the burn time was very long, and it took a lot of propellant. So here's the most efficient way you can get from an initial circular orbit to a larger outer circular orbit in the planar sense. So all the maneuvers taking place in the plane of the screen. And it's called a Hohmann transfer. It's an ellipse that's tangent, like I said, tangent at the bottom of that initial circle and tangent to the top at the outer circle. The way it happens, just the picture is repeated. What happens is you calculate the first delta V as shown down at the bottom. You've got the circular speed of that small circle. And then I've got V1, that's the velocity I need to get on that ellipse. And it's greater because it's a larger orbit. And I have to be going faster. So the difference between those two arrows, that's the delta V, delta V1. That's how much change in velocity that rocket has to produce for the first burn. When that happens, now you're on the solid elliptical line, and you coast, the satellite coasts up to the outer circle. If you do nothing, you just stay on the dashed line, you come back to where you started. Of course, you want to go into the outer circle, so you fire another rocket, lined up with the velocity. When I get there, I'm traveling at velocity V2. I want the circular speed, which is greater, so I need a second delta. So this has been done since the 60s, the 1960s for orbit transfers. This has been done for a long time with chemical propulsion. So now let's talk about low thrust propulsion, electric propulsion. So unlike impulsive transfers, low thrust propulsion, that trajectory results in an unwinding spiral because you start in a circular orbit, you produce this very, very low thrust, less than a Newton of force for these ion engines. And then you have this acceleration that just builds up slowly over time. So what happens is the circle just keeps getting slightly larger and larger and spiraling out. So the engine is burned continuously. Well, you're emitting these ions continuously. The engine is left on. And to look at why you want to do this, without showing the derivation, there's this famous equation down at the bottom called the rocket equation. If I can calculate how much delta V I want, I can divide that by the exhaust speed. Remember, that's G times ISP, and that's the exponent for the exponential function. If I do that calculation, that gives me the mass fraction. That's the final mass, the ratio of the final mass to the initial mass. So if I put in some numbers, let's just say the delta V is 4,000 meters per second. If I did that with chemical propulsion, that's the top one, ISP of 310, the mass fraction is 27%. That means if it starts out as 1,000 kilograms, and then I do the burn, I'm left with 270 kilograms. Well, a lot of it was propellant. What is that? 73% was propellant. If I do it with electric propulsion, the ISP is 3,300, 10 times greater. I put it in that equation, it's the same delta V, but now I've got a mass fraction of 0.88. So only 12% of the mass was propellant. So now I'm delivering a lot more payload to the target. That's, of course, always the goal. The problem is it takes a lot of time to get there. With the chemical propulsion, you fire the burn, and a couple hours later you're there. In the case of low Earth orbit to geostationary orbit.
So is MF is the final mass?
Yes.
Okay.
MF.
Because I've seen it as fuel mass. That's
yes.
Okay.
Maybe I should. A lot of people use MP for propellant mass. So one thing I'm going to talk about in a little bit is one of these issues is how to steer the spacecraft. You've got to steer this thrust. You've got this ion engine that's emitting ions, but you got to figure out how to steer it because it's not necessarily intuitive of how to steer the rocket. With the chemical propulsion, it's very clear. You line up the thrust, the rocket engine with the velocity, do the burn, and do the same thing at the other point. So let me define here. There's the Earth, there's the path of the satellite, the blue path. The velocity vector is tangent to that path. The thrust is the red vector, and that can be pointed anywhere in this orbit plane. So the angle between the green vector and the red vector, we'll call that phi, we'll call that a pitch steering angle, how to steer that thrust vector. And I can also have a different angle, alpha, but that's just the sum of what's called the flight path angle, gamma, from the horizon to the green vector, and then adding phi onto that. If I have this special case, if I use what's called tangent steering, it just means line up the thrust vector with the velocity, or let this angle phi be 0. And it turns out that maximizes the rate of energy. That's actually maybe a good strategy to start with. Here's a picture of what a low thrust transfer looks like if I simulate it on a computer and then make the plot. So in this picture, at the center, that would be the Earth. I didn't show the Earth, but there's the center of this plot is the Earth. The satellite starts out in a very low orbit, and you can't see it, of course, but there's thousands of revolutions. So this satellite is spiraling out very slowly, and to put it into perspective, the red circle is geostationary orbit. That might be my target. And you see it's not even there yet. And it's not necessarily going in a circular orbit. Even when it crosses that red circle, it may not be going in exactly the right orbit. This is what tangent steering. So it's slowly spiraling out. I had to solve this numerically, and I'll talk a little more about this later. But I had to solve the differential equations numerically.
You could, if you remember, we learned about the gravitational well of the Earth, and it's -1/r, and you have to climb out of that. Could we not think of those circles, if you imagine them pretty much like contour lines?
Right.
You're like looking down the middle of this gravitational well, and the contour lines are much closer together because it's steeper in the middle.
Right. It's harder to get out of that well when you're deep in it, when you're close to the gravitational attraction.
So you spiral more slowly.
You spiral more slowly, and as you build up energy and get out of that well, then your successive orbits get farther and farther apart because you're farther out of this well. So it's like a curved well. Think of it that way. But numerically, and I need to solve this numerically. I've got to solve the differential equations that essentially dictate F equals ma. I've got to solve that. I can only do it numerically, and when I do that, it takes what are called integration steps to do that numerical calculation. In this case, over 50,000 integration steps. When I run this, it takes a few minutes to run on a laptop. That's just to do one trajectory. So the point is, it's computationally difficult to do these calculations. Let me show very briefly some differences between the velocity change between impulsive transfers and low thrust transfers. Low thrust transfers generally require more delta V for 4 reasons. There are these different losses: geometric losses, steering losses, gravitational losses, and trajectory losses. So again, very briefly, geometric losses mean there are points where I'm turning the engine on and I'm thrusting points in the orbit where I don't necessarily want to be thrusting because the geometry is not suitable, it's not optimal. And as an example, if I do a plane change with an impulsive system, I have to do that at what's called a nodal crossing, where the 2 planes intersect. And that's the best place to do that. But if I'm using low thrust, I'm turning the engine on everywhere. So there are geometric points in the orbit where it doesn't make sense to fire the engine, but I just have to leave it on. Steering losses occur when I don't maximize the rate of change of energy. As I indicated, if I lined up the thrust with the velocity vector, I know from basic physics and mechanics that that's going to maximize the power. That's going to maximize the rate of change of energy. If I want to move something, a table, I want to push in the direction it's moving. So ideally, I want to line up the thrust with the velocity. But that doesn't always work because that doesn't necessarily achieve my target orbit. So at some point, I'm going to have to, what's called, create the orbit, create a circular orbit, circularize the orbit, the final orbit. Gravitational losses occur when I have to raise the satellite through the gravity field, and that anytime I do that, when the satellite is not moving horizontally with respect to the gravitational field, that's a gravitational loss. One way to get around that is to only turn the engine on when the velocity vector is perpendicular to gravity. But that wastes time to do that, to wait when those things, when that geometry occurs. And then there are trajectory losses. That's the last one. And one way to show that is, well, it's due to the fact that these are quasi-circular transfers. That is the spiral. The spiral is like a succession of circles that are building out. And one way to look at this is, if I do a Hohmann transfer from the starting circle is the inner circle, I ultimately want to get to the final orbit. If I just did it in one Hohmann transfer, and I don't show that here, that would be I'd have a burn here, half an ellipse and get to the very top and have that second burn, and in 2 burns I'd be done. But if I look at the case where I go to an intermediate orbit, I do a first Hohmann transfer and get to that middle circle, then create that middle circle. Then get down to the bottom again and do a burn and do that second dashed ellipse to get to the final orbit. So it'd be 4 burns total. And in fact, if you look at that, it turns out that the single Hohmann transfer takes a delta V of 3.9 kilometers per second. If I make myself go to that middle circle, it takes a total delta V of 4.3 kilometers per second. So it's worse. You're penalized for creating that middle circle. And if I keep doing that strategy and I keep making more middle circles, intermediate circles, it just gets worse and worse and worse. And in fact, I can do this and I can plot on the X the number of Hohmann transfers and the total delta V. And here's the very best case, just one Hohmann transfer. That's the lowest delta V. Here's that case I just showed with one intermediate circle. It's worse, and it keeps getting worse, but it approaches an asymptote. And it levels out, and in fact, that is the value, that's the delta V for low thrust, because low thrust has all these intermediate spirals, circles, all the way out. So let's move on to other issues associated with calculating low thrust transfers. I haven't really said how long the transfer time is, but if I go all the way back to that picture, that's 200 days. 200 days to go from low Earth orbit out to geostationary orbit. And a lot of satellite companies don't want to wait that long. But that's also a challenge of making this calculation. It's a 200-day transfer. So that's a problem, that's an issue. The other problem, and I think I've got a picture coming up, is every time the satellite goes in the Earth's shadow, the power goes out. Because the power is coming from solar arrays, so you can't run the engine. And that complicates the trajectory. The other problem is, when the satellite goes through the Van Allen radiation belts, the solar arrays become degraded. And it's not much of an issue if you only pass through it quickly, like a chemical transfer happens. But in that spiral, you're spending a lot of time in the Van Allen belts, and then the power can really go down by a lot if you spend a lot of time there. Another problem is you've got to constantly steer the satellite. So the fact is you've got to have attitude control to do that steering, and that just complicates the operation of the satellite.
Couldn't you avoid it if you launch in the summertime or the wintertime, where the tilt of the Earth is actually allowing you to avoid the shadow?
The belts, or the shadow, yes.
Yeah.
Yeah, that is true. It's a good point. The problem is, if I'm going to do a 200-day transfer, at some point I'm going to start to get back to the shadow condition. But you're right. You can do that so that when you get that bad geometry, you're high enough up and you're out of the shadow. So it is, there's a way to get around it. It's true. The problem is the initial part of that transfer, you're always in the shadow. There's no way of getting around Another big challenge is that this is powered motion. So you've got F equals ma, force is mass times acceleration, but the force is always there. And it's not a conservative force like gravity is. So I can't get an analytic solution. I can't get a simple equation that describes the trajectory. I've got to solve it numerically. So I've got to numerically integrate differential equations. And that's difficult, especially when it's 200 days worth of a spiral. So long transfer times, hundreds of or thousands of revolutions, very large computational load. And it's even complicated further by the Earth shadow and the solar cell degradation. And it's complicated by, I gotta know how to calculate how to steer this thing at every point in time. How am I going to do that? What kind of function am I going to have to figure out how to steer this thing, and not just to get to the target, but to get there in an optimal fashion, to try to maximize something or minimize something, like minimize the propellant needed. Here's a picture of the shadow condition. This is just my crude way of doing this with Microsoft Word. But there's the Earth at the center. Now let's say that's where the sun is at this particular time. So the sunlight's coming from that direction, and there's the Earth's shadow. So every time you pass in that gray band, the power goes out. And that affects the trajectory, and it affects the time it takes to get to the orbit. Because that's time you don't have any power. You don't have any thrust. All right, well, I just want to show these equations. These are the equations you have to integrate. This is really another way to write F equals ma. These are called Gauss's planetary equations. And these are the individual equations for the orbital elements, the elements that describe the orbit. So these are highly nonlinear equations, and you've got to solve them numerically to get the transfer. That's how I got that picture of that spiral, by integrating these equations numerically. And it took over 50,000 integration steps to do this, because the transfer time is so long. I'm not going to dwell on these equations, but if I look at them long enough, notice they all have these little f's. F sub r, f sub theta, f sub n. That is just the force in the three directions: the radial direction, the transverse direction, and the normal direction. So that tells me I have to know how to steer the spacecraft. Those are the components of force. And everything's got an F on it, except one term. There's a single secular term. That deals with this last equation, because that's the capital E is an angle. So that's telling us where it is in the orbit. And there's one term that does not involve thrust. All right, so the first problem, the first challenge, how do I even calculate the orbit? Well, one way to do this, well, maybe I should back up a little bit. I have to numerically integrate these equations. In general, you need 50 to 100 integration steps for each revolution. Well, I said there's thousands of revolutions. That's why there's 50,000 integration steps. Because I can't accurately propagate the trajectory all the way around a circle without 50 to 100 integration steps. The solution to this problem, I don't want to have 50,000 integration steps, is to use this concept called orbital averaging. So let me just talk about that briefly. I mean, this does involve some math, but I'll try to explain it in a simple fashion. The orbit has these orbital elements, and they are geometric elements like the size of the orbit and the orientation of the orbital plane and the eccentricity of the orbit, how skinny or fat is the ellipse. Those elements change very little from one revolution to another. You saw it in the picture, it just spirals up, so it doesn't change much from revolution 58 to revolution 59. So we can calculate the incremental change of each element over one revolution. So for example, calculate delta A, the change in, say, the semi-major axis, which is like the radius. Then get the average rate by taking that incremental change and dividing it by a time period, and let's use one period, the time it takes to go around one revolution. And now I get what's called an averaged or a mean rate. That's the average rate at which A is changing. And now I can propagate that average rate ahead in time and takes steps of several days. So now instead of 50,000 integration steps, I might get away with 50 integration steps. So I can take 5-day steps. And here's the equation that does that. So what you have to do is you have to put the original Gauss equations, the differential equation, in an integrand, change the integration variable from time to an angular position. That allows me to integrate the limits from, in the case of one revolution completely in sunlight, those limits would be 0 to 2 pi, once around the circle. If I'm in the shadow, those limits are where I entered the shadow and where I left the shadow. That integral is going to give me, in this case, delta A. It's going to give me the change in A. Then I take that and I divide it by P, the period. That's the mean rate. That's the average rate of semi-major axis. I know this is a lot to digest, just hearing about this for the first time. But I can do that, essentially I can do that for all of these ugly looking equations. And I get a mean rate of those elements. So maybe I won't go through this. It's a bit, I do that integration. It's only a function of one variable. I can use trapezoidal rule integration. When I do averaging, I've completely lost the ability to determine the exact location of the satellite because I've averaged over the angular variable. So that's one thing I have lost. I still have to know how to point the thrust as I go around that one revolution to do the averaging. Here's just an example of where I calculated the blue dashed line is precise integration. This is semi-major axis. Again, it's a radius-like variable. There's the transfer time. These are just 3 different cases, 3 different starting orbits. That green line is the Earth-Moon distance. So the blue dashed line is the true dynamics that have been solved with the brute force integration of 50,000 integration steps. The red line is using orbital averaging, and it's 100 or 1,000th of the computational effort. And you can see it matches really well. It predicts the blue line very well. And perhaps a better way to see this is eccentricity, because there's these oscillations at the end. And look, it's getting the average value. It's getting the average rate of that particular orbital element. So anyway, it just shows that the averaging is accurate enough to predict these trajectories. So challenge number 2, how do I point the thrust? I have to be able to point the thrust at every instant in that single revolution, even if I am using averaging. So let me just briefly talk about that. Again, this picture to indicate there's this angle phi, the angle from the velocity vector to the thrust vector. If phi is 0, then it's tangent steering. I'm aligning the thrust with the velocity. Well, here's where I'm going to just wave my hands and say, if you apply optimization theory, and if you apply some of these concepts that were being mentioned, like calculus of variations and optimal control theory, you can derive those 2 expressions for this is the optimal way to point the thrust, to steer the thrust. Optimal control laws, essentially, for that angle phi and an angle beta, which I didn't show, but that's an out-of-plane angle. And you can see that these equations are functions of these lambdas. And these lambdas are like Lagrange multipliers in optimization theory. Or in optimal control theory, they're called costates. And again, I know this is going much further out with background information on optimization and mathematics. But I can think of those Lagrange multipliers, or those costates, I can think of them as weighting functions. Because if those lambdas become large, then I'm going to put for example, if lambda E becomes large, I'm going to put all the steering effort into changing E, into changing the orbital parameter E, which is eccentricity. If lambda A is large, I'm going to put all my effort into changing A, which is semi-major axis, which is essentially the radius, the energy. So that's really just repeated here. Let me show some pictures. I think the pictures help. There's my ellipse, and the red vector is the thrust vector. And when lambda E is 0, that means I'm not putting any effort into controlling eccentricity. And I'm back to tangent steering. It's going to maximize the rate of change of energy. And it's going to tend to make that ellipse get bigger and bigger and bigger. On the other hand, if I make lambda E large, I should say a large negative value, then I get this kind of steering profile where it always points in the same direction. And the odd thing about this is the best way to steer if I want to maximize the negative rate of eccentricity. That is, create a circle. That makes sense because if I point the thrust this way, it's going around this direction. If I point the thrust this way here, that's going to tend to bring the apogee closer in to create a circle. The same thing, if I point the thrust this way, it's going to create the perigee larger. Again, create a circle. So that bottom picture is the best way to thrust to make the orbit more circular. The top picture is the best way to thrust just to keep making the orbit bigger and bigger and bigger. So it's the trade-off. So now I can figure out how to steer this thing by those equations if I just pick these lambdas in a smart way. Here's a picture of the out-of-plane steering, what's called the yaw angle, for different values of lambda I. And if lambda I gets really large, all the steering goes into changing the orbit point. So this now goes into the optimization strategy. So this is the approach I've taken to solve these problems. The idea is to parameterize the costates, parameterize these lambdas as simple functions with these little green dots, call those nodes. Assign them over time on the time axis. And if I only pick 4 of them, I can connect them by lines, use linear interpolation between those points. And now, when I guess those nodes, I'm able to get a history for those lambdas. And if I remember that, if this is lambda E, if lambda E of 0, that means tangent steering. I can always start my first guess with tangent steering. Then I'm going to get that picture that I showed. So it's going to spiral out. But it may not hit the right target. And it may not do it optimally. So the optimization program that I've set up, I guess these nodes, and I guess the trip time. I don't know how long it's going to take. That's a free variable. But when I do this, I have very few variables, less than 10. I might use 4 nodes for lambda E, 4 nodes for lambda I. Maybe I use 3. 3 for lambda E, lambda I, lambda A. There's 9 variables, and I got to guess the trip time. 10 variables. That's all I have in my optimization problem. It's a small-scale problem. Then I numerically integrate the transfer using that initial guess, using orbital averaging, and now I hook it up to an optimization algorithm. And again, I'm not going to give you any background on optimization, but I'm going to use sequential quadratic programming. It's a well-known optimization method. And it's going to search the design space and find the optimal lambdas, find the best lambdas that'll maximize or minimize the thing I'm interested in, like propellant load, and it'll meet the target conditions, like the target orbit. Because these optimizers have built-in constraint functions, or you can define the constraint functions. So I build that, and in summary, I've done this in MATLAB. I've used this strategy, and I've called my program SEPDOC, Solar Electric Propulsion Direct Optimal Control. And in fact, this was in a textbook that came out a year or so ago, assembled by a professor at Illinois. And he asked me to write a chapter. It's about this method on optimizing space trajectories. I use MATLAB, which is a mathematical software, and I use the optimization program fmincon. That's my optimizer. And I'm able to put in solar cell degradation effects, and I've done so by using this European Space Agency program, SPENDUS, to calculate how much the solar cells degrade, and then put that into my program. So, and I'm going to end here. There's not much to show in terms of what the output of this program looks like. It just gives you answers for what's the best transfer and what's the transfer time say from low Earth orbit to geostationary orbit. So I'm
Okay.
happy to take any questions.
I've got some questions, but let me summarize a few things for you guys, knowing what you guys have been through. This is obviously very complicated stuff compared to what we do in general physics, but it's basically solving Newton's second law, F equals ma, for when you're thrusting a spacecraft into space and you've got the gravitational force acting on it. So hopefully there were some terms that you recognize, like impulse. I mean, you have to give kicks of momentum to change orbits. We haven't, unfortunately, I should have somehow gotten to this, but there are 6 numbers that describe an orbit. And it turns out that those 6 numbers are basically because you're in 3-dimensional space, and to describe how something moves, we need initial conditions. Remember, like in our uniform acceleration, we have the initial position and the initial velocity, right, in x, and we have that in y, and we have that in z in 3 dimensions. So it takes 6 numbers to describe how something's going to move in space, and it turns out there's 6 little numbers that describe an orbit, and the reason there's 6 is for the same reason that we have initial conditions, like initial position and initial velocity in the problems that we've done. But of course, as I talked about, orbital mechanics and studying how spacecraft move and things like that, and planets move. This is very complicated stuff. But I think it's good to see complicated stuff, just to be able to realize that things get a lot deeper than what we do in general physics. But it involves, more and more complex ways of solving more complicated situations where you're basically solving the equations of motion, like F equals ma. So I hope you can get, you've got something out of it from that point of view, and I think you did a great job, Craig, of keeping a lot of the stuff simple. Some of it just can't be simple, though, because it's not, But I had a couple of questions, and let me say, by the way, I wanted to say this before. I want these seminars, there's going to be 2 more, to be really informal. So if you want to have a snack or something, just get up and get one. And I know some of you guys have to. I know you have places you've got to be at. So take a snack as you go. But these are always just for getting up and milling around. I can pay attention better when I'm walking around and eating stuff myself. So anyway, you bothered to come. You managed to get here. So have a snack. Take it with you if you want. I had a question. To try to relate this to what we've been studying in class, we were just talking about electrostatic forces, the electric field, and how one electric charge will push another electric charge according to the electric field, and these ion engines, you basically get a charged particle, and I want you to supplement and correct this. You have a charged particle, you ionize something, and that's what you do with the solar energy, right? Mm-hmm. And there's a finite amount of that. There is fuel that's going to run out, right?
Right.
Okay. So
you use it so slowly.
Okay. You ionize it, and then it gets pushed. Well, is it first pulled toward a grid, and then it passes through at the high speed?
That's
okay.
Again, I'm not a propulsion expert, but I think that's a good way to.
Okay. So you know how an electric field will push or pull on a charged particle. So these particles are ionized, which means they're separated into positive and negative charges. And then there's a grid there that's charged, that has a charge on it. So they're attracted to it, but they go right through the holes.
Right.
Right?
Grid has holes in it.
Yeah, and then they shoot out the other way. But one question I had was, is that if I can imagine a charged grid, like we're about to talk about capacitors, which are flat plates with charge. If you send a charged particle towards it, the electrostatic force is conservative, so it's going to accelerate it. But then once it passes through, if it's really a symmetrical field, it's going to slow it down on the other side.
And
So
I think the way that's handled is those charges are there's a negative opposite charge neutralizing beam that's sent at the exhaust.
Oh, okay.
Does that explain?
Oh,
it?
so they're okay. So they're
once they're
pulled
through the grid, then they're made neutral.
Then they don't see the
the field afterwards because it's neutralized. Remember the Faraday's cage and how you can neutralize inside of a conducting sphere, for example. There's no electric field, a charged sphere. You can shield by, and we were studying Gauss's law a little bit. Anyway, okay, so once it goes through, then it's kind of shielded on the other side. I wonder if that would be with an insulator. Could just do that.
I think they actually put let's see, electrons are going out, they provide some kind of positive,
Yeah.
positive particles are going out. There's an electron beam shooting at the